Hey there, and welcome. Today we're going to tackle a physics puzzle. One of those things that seems like it just shouldn't work, but it actually explains a ton about the world we live in.
I mean, think about it. It doesn't really make sense, does it? You toss a tiny little pebble into a lake and clunk, it sinks straight to the bottom. But then you have these gigantic 100,000-ton ships made of solid steel, and they just float. So what's going on here? Let's figure it out.
All right, to crack this case, we're going to have to put on our detective hats. There are a few hidden clues we need to uncover, and they're all around us. The first one? It's a totally invisible force that you've definitely felt, probably even today.
Okay, clue number 1 is called drag. And yeah, you can't see it, but trust me, you know exactly what it is. You ever try to run into a really strong wind or walk through the shallow end of a pool? That feeling of being pushed back, that's drag.
Now, before we get too deep into drag, we gotta clarify what scientists mean by a fluid. It's not just water or other liquids. In physics, a fluid is basically anything that can flow. That includes liquids, sure, but it also includes gases. So, the air all around us? Yep, that's a fluid. And this is super important because it means drag happens both in the water and in the air. So what exactly is drag? Really? It's just a fancy word for friction. But specifically, the friction you get when you move through a fluid. You know, when you're in a car and you stick your hand out the window? That force that pushes your hand backward? Yep, that's drag. It's always there, always trying to slow things down. Okay, here's where it gets really cool. The shape of an object makes a huge difference. Think about a streamlined, almost teardrop shape. The air or water just flows right around it, super smooth with hardly any resistance. But a big, blunt, blocky shape? It's like a bully. It has to literally shove the fluid out of its way, and that creates a massive amount of drag. And race cars are the perfect example of this, right? They don't have that shape just to look flashy. Nope. Every single one of those curves is engineered to slice through the air with as little drag as possible. So there's our first big clue. Shape is a huge deal when you're moving through a fluid. But what happens when you're just sitting in a fluid? That brings us to our next clue. It's a concept called density, and this is going to help us understand what's going on when something is just sitting there in a fluid, not necessarily speeding through it. Okay, the best way to get your head around density is to think about packing a suitcase. Imagine you have this giant suitcase, but all you put in it are a few t-shirts. Now, imagine a tiny little carry-on, but you've stuffed it completely full of heavy books. That second one, the little one packed with books, that's way more dense.
And that's pretty much exactly what density is in science. It's just a measurement of how much stuff, what scientists call mass, is crammed into a certain amount of space, or volume. The key takeaway here is that it's not just about how heavy something is. It's about how heavy it is for its size.
And of course, there's a formula for it. This little symbol here, that's the Greek letter rho, and it just means density. All this formula is saying is that you take the mass, the amount of stuff, and you divide it by the volume, the amount of space it takes up. That's it. It's just a simple way of showing the relationship between how much stuff and how much space. This chart really helps it click. So let's use water as our starting point, our baseline. We'll just say its density is 1. Now look at cork. Its density is way, way lower. It's not packed tightly at all. But then look at lead. Whoa, it's over 11 times denser than water. That means in the exact same little cube of space, lead has packed in 11 times more stuff than water has. It's incredibly dense. All right, so we've got our clues, we understand drag, and now we have a really good handle on density. I think we have everything we need to finally solve this float or sink mystery. So check this out. When you put something in water, it has to move some of that water out of the way, right? It displaces it. Well, the water doesn't just take that lying down. It pushes back. It exerts an upward force on the object. We call this the buoyancy force, or upthrust. And it's basically in a constant tug of war with gravity, which is always trying to pull the object down. And here it is, the moment of truth. It all boils down to one simple rule. If your object is less dense than the fluid it's in, the upward push, the buoyancy, is stronger than the downward pull of gravity. It floats. But if your object is more dense than the fluid, gravity wins that tug of war and down it goes. It sinks. Simple as that. And get this. This is the perfect aha moment. Our bodies, on average, are just a tiny bit less dense than regular ocean water. That's why we can float. But, you still have to work at it a little. But the Dead Sea, it is so full of salt that the water itself is way denser than regular ocean water. So when you get in, your body is suddenly much, much less dense than the water around you. You're like a piece of cork. The buoyant force is so powerful, you just pop right up to the surface. It's amazing.
So, there we have it. The key principles are density and buoyancy. And once you get them, you realize they don't just solve our little ship and pebble puzzle. They actually explain so much of what's happening all around us every single day. So let's just recap the awesome new physics toolkit we've put together. We've got drag, which explains why cyclists hunch over and why race cars are so sleek. We've got density, which tells us exactly why a light cork bobs on the surface while a heavy lead weight just plummets. And we've got buoyancy, which explains why floating is so much easier in the super salty ocean compared to a freshwater lake.
So this brings us full circle, back to the big question. If we know for a fact that a solid chunk of steel is nearly 8 times denser than water, how on earth do steel ships float? The secret isn't in the material, it's in the shape. A ship's hull is basically a gigantic, hollow bowl. And what's it full of? Air. So when you calculate the ship's average density, you're not just looking at the steel, you're looking at the steel plus all that incredibly light air inside it. That massive amount of empty space brings the ship's overall average density way, way down. So far down that it's actually less dense than water. And just like that, the ship floats, for the exact same reason a cork does. It's all about being less dense as a whole than the water it's sitting in. And that is how you float 100,000 tons of steel.